Hi everybody, we're just getting started here, but I wanted to pop on about, I don't know, I guess now it's 4 o'clock, but I wanted to pop on a little early just to check that the sound is working, so I'm just going to do that quickly and we can be on our merry way. Okay, you guys, so welcome back to another week of freemathhelp.ca brought to you by Scholarly Elite Tutoring. I hope you guys are having a wonderful day so far and that you're staying safe and having a good time. I know that as we get closer to the end of the school semester, people are getting a little tired of online learning. That's kind of what I've been hearing from our Scholarly Elite students, that people are just ready for the semester to be over, and I totally feel you on that. I know that it's been a long time of online learning, and we don't know yet what's going to go on for the rest of the school year. But I do commend you guys for keeping up with everything and just working towards your goals still, even though the school year has been a little bit off this year. But yeah, so anyways, without further ado, I wanted us to get started on our lesson. Today we're going to be talking about radicals again, but we're going to be extending the lesson that we did last time. Last time we talked about radicals more in a general sense, understanding what they are, adding and subtracting radicals, and also multiplying and dividing. Today we are going to be continuing on with that lesson, and what we're going to focus on in particular is the concept of rationalizing denominators. So this is something that we touched on last week just ever so slightly. If you did miss last week's lesson, I implore you to go back and watch the full lesson just so that you can get a better sense of what I'm talking about. I'm not going to go over too much of the stuff that we went on over last week, just so that people are not, people who did come here 2 weeks in a row, um, are not bored with the same content. That being said, it is there for you to watch, so I highly recommend it, especially if you are someone who did learn this unit online with just worksheets, because this actually is a unit that you do need to understand for grade 12 math as well. And actually for a lot of types of math, radicals are a really important part of math, and we use them in the physical sciences as well, including chemistry and physics, and they're really important for us to understand. So without further ado, we're going to get started here. So what we talked about last week, obviously when we think of rationals, we think of, this kind of thing. We've got like a root 3 or a root 40 or a root, x cubed, stuff like that. Now, as we learned last week, obviously everything that is a larger number or a larger, unknown variable inside of these radicals can be broken down. For example, this can be broken down into this. We've got root of x times root of x squared, and then we know that x squared, the root of x squared is x, so then our final answer is root of x, x times root x. So that's our final answer for that problem. Now, what we talked about last week is the fact that when we have a rational, and especially when we're doing divisions of rationals, because oftentimes they'll be in the framework of a, what's the word? A fraction. So I'm just going to erase this. We cannot have a radical sign in the denominator. So for example, if I had the radical term, such as a radical term such as this one. Wow, sorry guys, my brain today. What the problem is here is that it's bad practice to have a radical in the denominator of a fraction. When this happens, we want to multiply the numerator and the denominator by the same thing in order to clear the radical. And the way that we do this is very simple when it's something like this, where the denominator has just one thing in it, in this case a monomial, but it becomes more complex as we have additions and subtractions. So today we're going to start off with this example, and then we're going to move up to some more difficult concepts in this realm. And then afterwards, we're going to, if we have time, learn about rational exponents and also incorporating rational exponents with negative exponents for some more complex questions. So we've got a full day ahead of us. I'm actually pretty excited. As some of you guys know, grade 11 is my favorite grade to tutor for a number of reasons. And one of them is that it's where you get to learn some of the actually really cool fundamentals of math that you get to carry on into further years, such as calculus in university, even some linear algebra concepts as well. Anyways, so let's get started on this. We want to clear the denominator of the concept of root 6. Now here we've got 2 root 6, but in order for us to get rid of root 6, we don't actually need to multiply it by 2 root 6. Can I say root 6 enough? Probably. So just as a quick refresher, what we're trying to do here is the concept where when you have root, let's use, root x, for example, times root x, the root of anything times itself is just the thing inside the root. And I'll use a number to illustrate this a little bit better. So the root of, you know what, not root 2. So the root of 9, the square root of 9, times the square root of 9 is the same thing as saying 3 times 3, right? Because we know that's what that is. And it actually ends up being the number that's in the root. Well, that's what's happening every single time you multiply a root by itself, is that you're basically just canceling out the roots. So anyways, because I went over this last week, I won't go into that too much again. I do suggest that if you missed last week's lesson, just go back and watch the video. It's actually going to be very helpful for you in understanding this stuff. So anyways, okay, so what we want to do here, the first thing we're going to do is, obviously, we need to remember that when we have stuff in the numerator, it is technically in brackets, or in the denominator, however you want to put it. Basically, it's in brackets, and that's important to understand. And then our first step is going to be multiplying both the top and the bottom here by root of 6. As like I said, the 2 is not really relevant or necessary in most of these cases. You don't need to put the coefficient in with the radical. So let's do this piece by piece, just to make things a little bit more palatable. Now what's going to happen here is we're going to multiply this in FOIL style. So let's go ahead and do that. So let's do the first one. Root of 3 times root of 6. Well, that looks like this. You can put it under 1 root. And then we've got negative 9 times root 6. That's what that's going to look like. Oops. It could look a little nicer if my handwriting was a little bit better. There we go. Okay. And then on the denominator side, we've just got 2 times root 6 times root 6, which again can be put under 1 umbrella, we'll say. I'll just move this over to give us some space. Great. Now what we're going to do is here we've got root 18. And here we're going to keep this as 9 root 6. And then the whole purpose of this was to get rid of the root 6 in the denominator. And we know that anytime you have a root times itself, it's just going to become the number that's in the root. So now we're left with 2 times 6. Wonderful. Move this up over here. And let's take a look at what we're left with. So in this case, at this point, I've got root 18. That's an 18. Sorry, guys. And then minus 9 root 6. And then here I've got the number 12 in the denominator. What I want to do always in these scenarios, obviously our main goal was to rationalize the denominator, and we did that. And now at this point, what we want to do is actually break this down as much as we can and see if we can create a more simplified version of this problem. So let's go ahead and do that. In this case, I'm looking at root 18 and saying to myself, well, that can be further broken down into 9 and 2 because I know that 9 is a perfect square, and that's going to be helpful for me. I'm going to leave this part the same. And over here, 12 is also going to stay the same for now. We've got tricks up our sleeve. Also, I'm going to put those equal signs in. So now that we've broken this down, we know that this is the same thing as saying root 9 times root 2 minus 9 root 6 over 12. And I'm sure we all know that the root of 9 is 3. And so we're left with 3 root 2 minus 9 root 6, all over 12. And now I'm going to say to myself, okay, I've got a bunch of coefficients here, and I also have a number just by itself. How can I reduce this as much as possible to actually keep this as simple as humanly possible? And the way that we do that is by saying to ourselves, well, the number 3 goes into 3, 9, and 12. Well, negative 9 in this case. So what I'm going to do is basically say to myself, well, how can I reduce this all by 3? So I'm going to divide each piece here by 3 because I can do that in this scenario. So this is going to be left with root 2 minus 3 root 6, because the roots themselves don't change. Those are inside a little bracket, basically. And then this is what we get. And this is our final answer. So we're going to do some more complex problems, but basically I want to kind of reiterate what the steps were here. The first thing I did was I said to myself, what is the radical in the denominator? And that is what I multiplied the top and the bottom of this fraction by. In doing so, I created a denominator that does not have a radical in it, but I also created some new numbers in the numerator. And as such, I need to reduce that as much as possible because, again, the whole goal of math is to simplify things as much as we can, as much as humanly possible is what I was trying to say. And so that's what we did over here on this right side. We just kept reducing as much as we could. And then once we got a bunch of coefficients and numbers, we saw that they were all able to be divided by the number 3, and we did that. So this is kind of the first type of problem you'll encounter in this part of the unit. What happens is they then become much more crazy. So basically, about this last problem, dang it, there we go. Basically, it's just important to remember that when you're reducing the fraction, we can't just reduce the 3 and the 12 or the 9 and the 12. You have to look at everything and divide all of the terms. If they're not divisible, if they're not all divisible by the same thing, then you cannot do that. Okay, guys? This was not a stereotypical reduction of a fraction. This was really just us reducing the fraction all around. So that's something to note. Okay. Let us look at how these problems get a little bit crazier, and then we're going to look at how we incorporate the addition and subtraction symbols for this. Okay, so oh, dang it. Let's take a look here. We've got a pretty crazy problem. I'm going to start it up over here to have as much space as possible. So we've got 2 root 20 x to the power of 5. That's all under the root there. And that's subtracted by 12x squared, and that's all over 18x. Alrighty. So the first thing we want to do is simplify the radicals by finding perfect squares. So before we start rationalizing the denominator, first we want to go ahead and get these as simple as possible. So one thing we can do is separate numerators and denominators kind of in our mind and just go ahead and say, okay, well, 20 can be further broken down into 4 and 5, 4 which is a perfect square. Then basically this can be broken down into, oh, just one second. Sorry, I was looking at something and didn't see why it's missing something, but this can be broken down like this. Wonderful. So, and then we've got this side, which can be broken down into 4 times 3, because again, anytime something is divisible by 4, it's likely that 4 is going to be that number that you care about. And then in the wow, that was a terrible straight line. Gosh, sorry guys. Not that this one was any better. Oh my goodness. It's really hard to draw a straight line on this. That's the one thing that I find difficult. Okay, so then this part is going to be in the denominator. We've got 18 is divisible by 9, 2, and then the x is just by itself. Wonderful. So let's break these down as much as we can. Here, the 2 on the outside is going to stay. The root 4 is going to become 2 on the outside because the root of 4 is 2. And then we've got the root of x squared, which is x. And inside, actually here I can break this down into x squared, and x, just to make this easier. So x squared, and then this other x squared has another x. And then inside, all we're left with is 5 and x. And then over here, we've got 2, and then 3. Oh, sorry. 2, and then x, because of the x squared. And then root 3 on the inside, because that's not a perfect square. And then here on the denominator, the root of 9 is 3, so that goes on the outside. The root of 2 is some crazy situation, so we're just going to leave 2 and x on the inside. And then to get the simplified version, 2 times 2 is 4, and then we get x squared. So at this point, your equation should look something like this. And if anyone is confused, please feel free to leave a comment in the chat. I try to be as I try to put as much of an explanation as possible into each step, because what I used to hate in math class was that teachers sometimes would not explain how they got from one step to the other. So I try to do that as much as I can. That said, I know I'm not, nobody's perfect. So please let me know if there's something I missed or you didn't, you wanted me to go over, okay, guys? So at this point, what we've got is that we're going to try to rationalize the denominator because we've simplified it as much as we humanly can, and that's kind of the best next step for us. So in this point, we're going to go 4x squared times root 5x. Actually, one of my students a long time ago taught me this really cool trick where if you want to know where the root ends, you put a little nick there. Anyways, I just thought that was cool. It's something that would be helpful for some people. So there we go. That's a 3. And then all of that. These straight lines are really getting me today. Honestly, I would put a straight line from the little straight line maker, but it's actually an arrow, not a straight line, which is very annoying. So anyways, just like in our last problem, what we've got here is a denominator with a root, with a radical. And that's a problem because it's bad form to leave it like that. So we're going to multiply it by root of 2x on both the upper part and the denominator. And again, we don't bring the coefficient into that because it's really not necessary. We're just trying to get rid of the root of 2x so that we can make it 2x. All right, guys. So again, this is done like this. You're multiplying this like this. You're multiplying this like this. And basically, just like with our lesson last week, the inside of the radical gets multiplied by the inside of the radical. Okay, guys? So that's going to look like this. 4x squared times root 5x times root of 2x is going to be 4x squared times 5x, or root 5 of x times root 2 of x, just like that. And then again, so the outer part of the radical stays where it is. So then we've got this. Okay. And then here, root 2 of x times 3 root 2 of x becomes root 3 2x times 2x, which is going to just become 2x in the end. So put my equal signs in. Oops, because I don't want to lose marks if I'm on a test. And from this point, we're just going to go ahead and get all of this together. So 4x squared, 10x squared. And we've got, so again, like all of our exponent rule stuff applies. Nothing has changed in terms of how the math is done. It's just that there's a little extra step where we have to rationalize the denominator. And keep this in mind. This is not just something that you're doing for this unit, for this thing. You need to do this anytime you have a square root in a denominator. You have to do this type of work, because it is, like I said, it's not considered proper math form to leave it the way it was with the radical in the denominator. So anyways, now we're here, And I'm just going to move this up. So I hope, and if I'll bring this back up later so everyone can kind of take a look. So, or actually I'll just give you guys like 5 seconds to copy out all that down. Okay, so let's bring this down a bit and keep on going just to get, and again, like these problems do take this many steps. They are annoying. But what's nice is that once you get the hang of them, it's actually really easy to get really good marks on these tests once you kind of have practiced these enough. So alrighty guys, let's keep up with this here. So what we want to do now is simplify everything. So let's go ahead and start with the numerator. 4x squared can stay the way it is. We want to break the 10 down at the 10x squared like this because we're going to actually get rid of the x squared, put it on the outside in a minute. 2x, and then the root 6x cannot be broken down further, so I'm going to leave that. This bottom part just becomes 6x. And here, this part, the root of x squared is just x, so I bring it to the outside where it's going to be 4x squared times x, which is eventually going to become 4x cubed, but we're just going to show the step like this for now. Then on the inside, we've got root 10. Over here, we've got 2x minus 2x times root 6x. And this is chilling the way it is. So now we can actually just keep on trucking. We've got one last step here. First, well, actually, before we do the one last step, what I am going to do is show you that this becomes 4x cubed, root 10 minus 2x, 6x, and then there we go. So now what we can do, just like we did earlier, is simplify this and reduce it by dividing each term by 2x, because as we can tell, all three of these coefficients and or numbers can be reduced by 2x. So if I was to do that, I'm going to be left with 2x squared here. Remember that the radical stays the same. And then here, we're just going to have minus root 6x. And then here, we're left with 3x. Oh, sorry, just 3. Okay. So there we go, you guys. And as we're rationalizing, it's really important to constantly check the problem to see if it can be simplified more. We have to ask ourselves, like, can the fraction be reduced? Can the radicals be simplified? Like, these steps may happen several times on our way to the solution, and it's always good to just be reducing as much as you can, okay? So that's something to keep in mind. And up next, we are going to be learning how to do something a little bit more complex. So I'll let you guys just keep writing those last few steps there, and then we can go on to our next problem, which is where the next problem is where things are going to get a little bit more interesting, because we are going to be simplifying when we've got binomials with an addition in them. Okay. Alrighty, guys. So like I said, things get a little bit more complex when you have a problem such as this one. Say you have 2 and then root 3 minus 5. So remember what I was saying earlier, that like if you have a term in a numerator and or a denominator that's like this, that has something with like either an unknown variable or a radical in it, plus or minus some number, technically this is in a bracket, because whatever's in the denominator is kind of on its own situation. Now, one thing to also keep in mind is, just like I was saying a while back, and I don't know if it was saying to you guys or to the grade 10s, but what it means is that, like, you know, in a situation like this, nothing can be canceled out, because this is its own thing and this is its own thing. You can't cancel the x's out, you can't cancel the 5's out, because they're together and they're not exactly the same. So that concept applies here. And what we're going to do, you know how up until now we've just been multiplying by the same radical that's in the denominator? Well, right now we've reached a standstill of sorts wherein we cannot do that, because, and I'll show you why. If we were to do the thing where we just multiply by the root in the bottom, as it is, so in this case we've got 3 minus root 5, and then root 3 minus 5. This part here, not right. I'm just showing you why it doesn't work, okay? So this is not something you're supposed to do. I'm just showing you how it's wrong. So in this case, if we were multiplying the denominator by root 3, we would have to distribute it, and we would have to end up with 3 minus 5 root 3, so that's what we're not going to do. We also cannot multiply it by this, because it's going to create a problem where we get, so 3 times root 3 is 3, then root 3 times this is 5 root 3, then this is going to be, again, negative 5 root 3, and this is going to be plus 25. Okay, so in this scenario, what's going to happen here is that you get 3 minus 10 root 3 plus 25, sorry, and now you have another radical in the problem, which is what we're trying to avoid in the first place. So, like I said, that's not the right thing to do. I just wanted to show you guys why we don't do that. What we are going to do is multiply it by its conjugate. So a conjugate is made up of the same terms, but with the opposite side in the middle. And what that looks like is this. So you get root 3 plus 5. Root 3 plus 5. Okay? This is a really important concept in math. I need you guys to kind of, if you have questions about what I'm doing, ask me them, because this is really your opportunity to get this down pat and have yourself 10 steps ahead even for next year. Okay, guys, so we're going to distribute the numerator and do the difference of squares in the denominator. So let's start with the numerator. 2 times root 3 is going to be 2 root 3. And then 2 times 5 is obviously 10. Cool. And then here we've got to do our difference of squares. So root 3 times root 3 is 3. Root 3 times positive 5 is positive 5 root 3. Negative 5 times root 3 is negative 5 root 3. And negative 5 times positive 5 is negative 25. Alrighty, so that's the first step. Now what we want to do is simplify the denominator. So as you can see, we've done a difference of squares here, which is awesome, but we do need to figure that out. So we've got 2 root 3 plus 10 staying in the numerator. And then here, positive 5 root 3 and negative 5 root 3 are going to cancel each other out. So we're left with 3 minus 25, which, as you can imagine, is going to be negative 22. And just as always, as we've done every step of the way for this, we need to determine if this can be reduced. So in this case, all 3 things can be reduced by the number 2. So this is, and actually by negative 2, which is important. So what we're going to do here is get negative 2 root 3, because we never want to have a negative in the denominator, right? So this is the best way to do that. And then negative 5 over 11. And this is our solution. So this is our final answer. So this is how we use a conjugate to rationalize the denominator. So like I said, you don't use the same term that is in the denominator at the beginning. You multiply it by the same terms but with the opposite sign in the middle. And we're going to do some more examples because obviously this is a bit difficult for a lot of people when they first start out. So let's take a look. I'll give you guys like 5 seconds just to do that. Okay. Alrighty guys, so let's try another problem. Let's do one that's a little bit more complex. And if anyone finds that the jump from this problem to the next one is too much, we can go back and do something that's a little bit easier. But I figure I want us to maximize our time together here, so we also want to try some that are a little bit harder as well. Oh gosh, okay, let me just rewrite that. Sorry. Alrighty. So say we've got 2 times the root of 20x to the 5, just like we did in a couple questions ago. Oh wait, no, sorry, I'm looking at the wrong thing. This is later. Okay. Let's try a problem such as this one. So in this scenario, we've got 3 minus root of 5 and 2 minus root of 3. And the reason we're doing this one, even though it's somewhat similar to the last, is that sometimes when the teacher flips these around, people get a little bit confused. So what's the best thing to do is just practice as many different types as possible. So okay, let's try this with our different signs. So this is 2 plus root 3, 2 plus root 3. And remember, this was not the initial problem. The initial problem was just this front part by itself, right? Now, sorry, just give me 1 second, you guys. I apologize. Alrighty, sorry about that, guys. Alright, so when we're doing this problem now, we still have to follow our normal FOIL rules. So we're going to start at the top here. Actually, let me get rid of these lines to make it a little easier. So 2 times 3 is 6, obviously. And then 2 times negative root 5 is going to be negative 2 root 5. And then on this side, we've got 3 times root 3. And that's positive because this 3 does not have a sign in front of it, and so we always assume that it's positive. Then we've got negative root 5 times positive root 3, and that's going to give us negative root 5 times 3. And now on to this side. So we've got 2 times 2 is 4, obviously, and then here we've got negative 2 root 3. Then we've got positive 2 root 3, because again, that's the whole point of the conjugate, is to create this perfect square where, the difference of squares that's going to cancel stuff out. And then root 3 times, positive root 3 times negative root 3 is just negative 3. Okay, guys, so moving forward, Up here, sorry, on the numerator, all we're left with is the following. So 6, ow, and then we've got minus 2 root 5 plus 3 root 3 and minus root 15. And then here we've got this part canceling, and then we're left with 4 minus 3. So our final answer at this point is just going to be this same thing. I'm not going to rewrite all this, guys. I'm just going to do 1. There we go. Save us all some time. And because this is all over the number 1, we can actually just write this like this. 6 plus 3 root 3. And I'm just going to put them in order of increasing radical size. Like that. Doesn't really matter because that's how math works. If you're adding stuff, it doesn't really matter what order you put it in. Typically, the best form in, you know, polynomials when you're doing that kind of unit. Oh, on the last question, when you divide it by -2. Oh, Allison, I'm really sorry. I just saw this. I just saw your answer. On the last question, when you divide it by -2, why did we end up with -2 on the first part of the numerator? Let me go back to the last question just so I can answer that. I apologize. I just saw that question. Thank you for asking questions, you guys. I really appreciate it. It makes me feel like people are in the chat, which is awesome. So when I divided by -2, why did we still end up with -2 on the first part of the numerator? Okay, this is why. So we have, let's say we're doing this all separately. So let's look at the numerator, and then we'll do the denominator separately. Okay. So in the numerator, what's happening here at this point is that I've got 2 like this divided by -2. And then here I've got +10 divided by -2. And then here I've got -22 divided by -2. Okay, so the reason we end up with the negative on the first part of the numerator is because I'm dividing by -2 all around. This is actually just going to give us... Oh, I see what you're saying. It's not supposed to be a 2. It's supposed to be 1. You're right. I'm so sorry, you guys. In my haste, I did not realize that. Allison, you're totally right. Thank you for checking me on that. This is 100% going to become -1 root 3. So that final answer was incorrect. I apologize about that. Thank you so much for checking that. And I appreciate you asking, honestly. Sometimes because I'm talking, I don't realize what I'm doing on the little mistake side. And I really do appreciate when people remind me to check myself before I wreck myself. So that's actually -1. So you're totally right, Allison. Thank you for calling that. That's actually the best way to put it. So you guys are awesome, and I appreciate you, you know, actually getting the answers correct, which is the best thing you're supposed to do. Okay. So hopefully that makes more sense. Obviously it makes sense to you. You clearly saw what happened there, that I got it wrong. So thank you for checking that again. Sorry, I sound like a broken record. Okay. Alrighty. So guys, let's go ahead and try something a little bit more complex, and that is where we have 2 of these more complex radicals in the problem. So hopefully that helped, or at least clarified that I made that mistake. Again, I apologize about that. So we're just going to try this one here. So we've got 2 root 5, 3 root 7, all over 5 root 6 plus 4 root 2. Okay. So this is going to be either our second last or last of these problems, and then hopefully if I have time, we're going to go on to rational exponents, because that's also a really intense unit. Sometimes the teachers actually roll these 2 units together. It just depends on your teacher and your school, but yeah, definitely 2 very, very important units because they carry on into grade 12 and other stuff. So what was I going to say? Yes. remember that we always need to look at the denominator. That's what matters, because that's what we're trying to fix, is the denominator. And so in this case, we've got 5 root 6 plus 4 root 2, and by way of everything that we've learned so far, we need to multiply by the conjugate, which is 5 root 6 minus 4 root 2. So I'm actually going to show this as a separate step, just because I know that for some people having that visual helps a lot. So 5 root 6 plus 4 root 2. And we're going to multiply by the conjugate on the numerator and the denominator. So that's going to be this. Okay, guys. So now all we need to do is FOIL in the numerator, and the denominator ends up being a difference of squares. So that's kind of something that can save you a lot of time, is that you will know that the denominator is a difference of squares. In this particular instance, what we're going to do is jump to that next step, just so that we can kind of illustrate how I would suggest you do this in class, on a test, I mean, because as you can see, these get to be very long and quite complex, and you don't want to waste time showing every single step at this point in grade 11. That's not to say that in general you don't get marks for showing steps, but this step that's in between this, where you're foiling stuff in the denominator, it's not really necessary. In fact, the teacher actually would probably be more impressed that you automatically jumped to a difference of squares. But again, every teacher is so different, and it's hard to say like steadfast answers to things, so I try not to give too much general advice in that sense. Anyways, let's just get to the question. So we've got 10 root 30, and then here, that's going to be minus 15, and we've got, wait a second, what am I looking at? Oh, yeah, okay, sorry. I thought I had put the wrong numbers for the wrong thing. Anyways, not the point of the story. So the point of the story is this. This is here. This is going to be negative 8 and root 10. And then last but not least, we've got positive 12 and root 14. Okay. Up next, in the denominator, all that we're left with is 25 times 6, because the 5 times 5, and the root 6 times root 6. And then we've got minus 16 root 2, or times 2. So as you can see, I kind of skipped the part where I show the middle step. That's kind of what I was talking about, is that you want to kind of indicate that you understand that this is a difference of squares, and that the whole reason that we're doing this is for the difference of squares. You know how it is. Okay, now we just have to simplify realistically. There's not too much left at this point. I'm going to skip a step here in showing like the denominator multiplication answer and just get the subtraction answer. If you're confused by what I mean, feel free to drop a question in the chat. Also, if I'm lagging today, you guys, I'm really sorry. I don't know if it's my neighborhood or what is going on with the internet. It is literally the worst internet I've had since quarantine started. We literally almost didn't start the grade 9 class because it was just so bad. But hopefully things are okay on your end and that you can hear me okay. Just note that I will say, if ever the internet is so bad that we're lagging the whole time, please do let me know. We want this to be a really positive experience for you guys, and so I'd rather skip a week where we don't have good internet instead of having it be like, you know. I just want to make sure everybody can get the access to the questions and the stuff that they need. Anyways, that is the answer. I know that this one actually seemed a little bit shorter, but the reason it seemed shorter is because I kind of skipped some of the mini steps. And again, I actually recommend in your tests or whatever, your assignments that you're doing, take a look at how much a question is worth and then discern based on your own judgment whether or not it's worth showing every little step. I personally don't think that in grade 11 you get extra marks for showing the difference of square step, just from what I've seen. But again, it depends on your teacher. So anyways, I'll give you guys like 2 seconds to write that down if you're following along on paper, and then we'll move on to the next part. Alrighty, so moving on. Oh, guys, you have no idea. I get so much enjoyment out of teaching the grade 11 class, and every other class, I wish that I had this much joy about it. It really is my favorite grade to teach. I hope that you guys are benefiting on some level from the stuff that we're going over. I try to pick stuff that I remember for my own self was really confusing in high school, and also just from years of tutoring, like seeing what problems kids found confusing. So it's 4:45. Let me think. You know what, guys? We're just gonna go ahead and go into the next part of the lesson and not do another radicals one. And then if we have time, we'll go back, or even next week we can just do a little bit of a refresher. But I really want to make sure that we touch on some exponent law stuff in the next 15 minutes, so that can make a little bit more sense for you guys. And then maybe next week we'll do a bit of a refresher just so that everyone has mastered it. And yeah, and then if you're one of our students and you want me to send you some radicals questions, feel free to let me know. I'm happy to do that. Usually your parents have access to contacting me. If you're not one of our students, feel free to go to the Scholarly Elite website, and if you want to sign up for tutoring, you're more than welcome to. But yeah, so basically we're going to talk about a couple of the exponent laws that are more important for grade 11. So we've got 2 things that we want to touch on. First is the negative exponent law, which is something that some grade 9 classes do touch on, others don't. It really just depends on who your teacher was. So negative exponents are basically an indication to us that whatever the base is on the wrong side of a fraction. And I want to make this very, very clear, because I found that when I was tutoring, a lot of the time kids would just think that it means you flip the fraction. So as a result, I like to use a bunch of different examples to kind of illustrate what it is I'm talking about. So first of all, let's just look at a simple example. Let's look at the example of x to the power of -3. In this example, because x is just by itself, I can automatically assume that x is over the number 1, the same way that any number would be over the number 1. The number 4 is over the number 1. The number -321 is over the number 1. All numbers, when they're by themselves, are technically over the number 1. They're all technically fractions. So when I've been given a problem such as x to the power of -3, I automatically know that it's technically over the number 1. And I know that my negative exponent indicates to me that the base that it's attached to, in this case, which in this case is x, is on the wrong side of the fraction. So what this is actually going to look like is 1 over x cubed. Now, one thing that's really important to note, like I said, this fraction did not flip. What happened is that I just moved x to the other side. I'm going to give you an example to illustrate what I mean. So for the next problem, we'll call this problem A. For problem B, let's take a look at something like 5y to the -2 over 4. So in this situation, as you can see, we actually have something in the denominator that's not just the number 1, and I have a coefficient attached to y. But in the situation where y is on the wrong side of the denominator, I don't move anything else. Everything else stays as it is. I just move y. Okay? So that's really, really important to remember, because it is something that comes up over and over and over again. Let's take a look here. Let's do a problem such as this one. So say I've got b to the -3 times b to the -2. So using our product rule, if you guys remember from grade 9, and actually if you're not feeling confident about your exponent laws, I actually did exponent laws, like the base exponent laws, with the grade 9s today. So if you want to go and watch the first hour of the video that's going to be loaded onto our YouTube channel in a couple of hours for the grade 9 and 10 class, the first hour is all about exponent laws. And it's actually a really great way to just refresh your memory on it, because I know that it's been a while since you guys probably have seen exponent laws. So as you remember, or you may remember, there's something called the product rule. When you have a base multiplied by the same base, you add together their exponents. So in this case, I'm going to go b to the -3. And what confuses a lot of people is like, well, they're negatives, so what am I supposed to do? Do I flip the fraction first? You don't flip the fraction first. Leave the flipping until the end, okay? So we've got b to the power of -3 plus -2. Which obviously, using integers, we know that that's just going to become this, and then this becomes this. And now that we've simplified this as much as possible, we can put it into its most correct form, which is that. And that's our final answer. So hopefully that makes sense for you guys. I'll just move this over so that we can keep on trucking here, so everyone can write stuff down if they want. All right. Now, we're going to do one more problem like this, and it looks something like this. So we've got y to the -3 divided by y. So again, in problems like this, a lot of times when I was tutoring, I found that kids would jump to the conclusion that we should do the flip first. My method of teaching is that I don't want you guys to copy stuff. I want you to copy down what I'm writing. That's going to be helpful for you. But I mean, I don't want this to be something where you're copying an exact algorithm. I want to teach you guys strategies that you can use to solve all the time, so that you're not just looking for exact types of problems. You know what to do in any scenario. So that being said, one of the main tips I have for exponents is don't flip the fraction, don't do the negative flip until the end. So right now, because I know my quotient rule is that when I have two bases that are the same being divided, you've got to subtract their words, their exponents is what I'm trying to say. Sorry guys, I've been talking a lot today. So we've got y to the -3 minus 1. And that just becomes y to the -4. And this becomes 1 over y to the power of 4. Okay guys, so that's the negative exponent rule. I know that it's not anything too crazy, but I do think it's important to go over, and just to go over that thing about leaving the flipping until the end. Because as we go on to some crazier problems, which I wish we had time to do like way more. I will hopefully next week. We're going to next week do like very, very intense problems for both the first part of this lesson and the next part of the lesson, just so that everyone can feel confident. All right. So guys, next we're going to learn about something called rational exponents. You know that a rational is basically a number that has like a numerator and denominator. So I will show you what I mean by rational exponents. Okay, so a rational exponent looks like this. Say I had n to the power of 3 over 2. Wonderful. So what this is whenever I have a rational exponent, it's the same thing as saying the following. Whatever is in the denominator of the exponent is actually what's in the root. Whatever is in the numerator of the exponent is actually what the number is being brought to the power of. So when I say it's in the root, this is different than a coefficient of a radical. So on your calculator, and I know everybody has a different type of calculator, but my calculator is pretty standard, so I'll kind of go based off of mine, and then if you have something totally different, just let me know. On your calculators, if you look at the numbers that are above, like that are not on the buttons, but that are above the buttons, you should have one that if you were to press shift on that above number, it's like a square root sign with an X in it. Okay? that's where you indicate this thing that I'm talking about. So if you have your calculator in front of you, I want you to do this. I want you to go shift 3. Oh, wow, what did I do that? Oh, not shift 3, sorry. First press 3, sorry. And then do shift, that little X with the radical, with the root sign, and then press 27. And the answer should be 3. That is because the third root of the number 27 is 3, because 3 times 3 times 3 is 27. We also call that the cubic root. You could call it the third root, the cubic root. It doesn't really matter. But basically, that's how you can specialize the root in your calculator. So, keeping all of that in mind, right at this moment, you don't need to do that. But I just kind of want to indicate this to you. So, one thing that's also important to remember is that anything to the power of a half is the same thing as saying square root. Because the square root is the root, basically the root with the 2 inside the root sign. Okay? So, 9 to the power of a half is 3. Because this is also equal to 3, which is the same thing as saying this. So, this is really important to not mix up. It's something that, like, the main stuff that I would see with students in terms of losing marks on tests is that they would mix up which one is the numerator and which one is the denominator and which one goes where. Basically, I just like to think that the roots are in the ground, so the root is on the bottom. Okay? That's how I remember it. You don't have to remember it that way. I just am a person who likes verbal explanations of things, and I like having kind of a narrative in my mind about how things work. Okay, so let's do a problem that's a little bit more complex within this last 3 minutes. And then next week, please, if you are interested in learning a little bit more about this, please do, what's it called? Come back next week. We're going to do some pretty intense stuff, and I'm going to teach you how to actually solve every single time in a way that's strategically correct, so that you don't have to memorize a bunch of million different ways of doing this. I'm just going to try to simplify it as much as possible. So, in our next few minutes, let's try this problem. So let's say we have y to the power of 4 times 3 root 2. To the power of 3 root 2. So as you guys remember, with our power rule, we have to multiply this in. And then what ends up happening is you get y 4 times 3 over 2. And we know that the number 4 is technically over the number 1. So this just becomes y 4 over 1 times 3 over 2. And this becomes y to the power of 12 divided by 2. And the simplification of that is naturally y to the power of 6. So that's this problem. Okay. Yeah, so we're going to do one more that's a little bit more complex, and then we're going to call it a day. But like I said, if you are interested to learn kind of the real tricks on how to do problems like for example, we're not going to do this problem right now, but next week we probably are going to do this problem. So x squared y to the negative 2 over yx to the power of negative 7 over 4 all to the power of 4. So we're going to do problems like this and even more complex ones next week, so stick around to learn that kind of stuff. But I will quickly do one more problem here. So we've got 27 p to the power of 6 times 5 over 3. So if you recall with our extended power rule, and again, if you're confused by the powers and the exponent laws, please do feel free to watch the grade 9 video from today's freemathhelp.ca grade 9 video. It should be up in the next few hours or tomorrow. We do go over everything, and so it'll be helpful for you. But remember that we have to treat 27 as its own base. This is 27, not 27. So what we're going to do is go 27 technically is to the power of 1. So when you multiply that by 5 over 3, it's just going to be 27 to the power of 5 over 3. And then here we get p to the power of 6 times 5 over 3. And what ends up happening now is that what we need to do here is the following, because we need to solve this. So this is going to become third root of 27 to the power of 5 times p to the power of 10, because this is going to be canceling out. Okay. Now, to solve this, what I want you to do again on your calculator is first type in 27 to the power of 5, and then you're going to get the third root. So you're going to press 3, upper button for that little x with the root, square root there, or some calculators have root 3 as a button on its own. If yours does, you're fancy, and I don't know what to tell you, that's pretty cool. Then you're just going to put the answer inside the root, and you should get 243 as the final answer for here. And then this p to the power of 10 stays the same. Alrighty, you guys. Okay, so that's our final problem for today. I'm going to leave that up for like 30 seconds, and if anyone is here for the grade 12 class, welcome. We're going to get started in about a minute. But if any of the grade 11s have questions for me, please feel free to drop a question in the chat, and I'm happy to answer it before we start the grade 12 class. And I'm excited to see you guys again next week, because this is really one of my favorite units to teach, because I just believe that there's a simpler way and that you don't need to be stressed about it. So anyways, yeah, thank you to the grade 11s. Hope you guys enjoyed, and we'll see you guys again soon. Have a safe week, and stay healthy, and just, you know, stay home. Have a good one. Okay. So I'm just going to take my grade 12 stuff out here. Put the grade 11 stuff away. Alrighty. So my grade 12s, I hope you're having a great day so far. We are back in action doing some trigonometric graphing again, some trigonometric graph applications today. So I'm pretty excited about that. Before we get started on the trig graph applications, I feel like I would be remiss if I didn't let everybody... Oh, no problem, Allison. Thanks so much. I really appreciate you joining the class. Hope you guys have an awesome week, and we'll see you guys next week, okay? Awesome. So, what was I gonna say? Oh yes, I want to pull this here. Oh no, I've already set up something, so we'll just go back. We shall go back. Come on. 10. Okay. So remember last week we were looking at graphs, and we were given the equations, and we were being asked to create the graphs. Well, this week we are going to do the opposite, which is that we are going to look at these equations and we are going to solve the graphs. So taking a look at this equation, at this graph here, one thing I want to make very, very clear, first and foremost, is just to reiterate what our equation is that we're even looking for. So when we talk about graphs of a sinusoidal nature, meaning that they repeat themselves, that's a periodic graph. I mean like sinusoidal, like these ones that are for the waves. What we are doing here is we want an equation that looks like this. Either y equals a sine k x minus d plus c, or y equals a cos k x minus d plus c. So on a sine graph, the graph should start at 0. On a cos graph, it should start at 1. And by 0 and 1, I mean, if it starts at its peak, then it's a cos graph. If it starts at its sine, if it starts at its midpoint, then it's a sine graph. So if you were not here last week, feel free to stick around. I do recommend, though, going back and watching last week's lesson, because a lot of the stuff that I'm going to talk about will make much more sense to you in that way. So yeah, so what we're going to do for this one is, this is actually kind of a word problem that we've been given. So I'm just going to type this in here. So okay. So here we go. We've got this graph here. So the piston of an engine moves up and down along a crankshaft in the middle. The height of the piston over time is shown by the graph. So one thing I do want to make clear, because I actually graphed this on Desmos. So this is this. And then this is the time in seconds. And this part here is the height. And that's pretty standard that time would be our independent variable on the x-axis, but just wanted to make that clear for you guys. Great. So what they're asking us to do are a couple different things. So first, what I'm going to do is just move these up if I can. Oh, no, not what I was trying to do. This part. I'm going to move that just so that we can recall what we're talking about. Okay, so the first question that is relating to this is, how long does it take for the piston to move up and down once? Let me just make that clear. Oh, clearly not what I was trying to do. We shall fix this. Give me 1 second, you guys. Whoa. Oh my gosh, that's so annoying. Okay, there we go. Wonderful. How long does it take for the piston to move up and down once? So, as we discussed last week, there are a couple different variables and factors that we need to be concerned about. So, in our equations, we have the letters A, K, D, and C. So, A is the amplitude, which tells us how much of a vertical stretch there is. And then the K tells us the phase, not the phase shift, the vertical, oops, let me fix that. The K tells us the horizontal stretch. Also, it can tell us the period, which is how long it takes exactly for the equation to repeat itself. So what they're really asking in this question is, what is the period? That's actually really easy to solve for. So what I want you guys to remember when you're solving for the period is that you want the graph to go from the starting point and back up to the starting point, okay? Or just back to its starting point. So at this here, we've got the starting point up here. It goes down and it comes back up, and we're back at that same y value here, which tells us that it takes the piston 1 second to go up and down one time. And that's really what we can also say is the period. So the period is 1. Okay, so I'm going to erase some of this just because I want to get rid of that line there. Great. So that takes 1 second. And if you guys have any questions about the stuff that I'm writing down, feel free to leave them in the chat, okay? And if you have questions that don't have anything to do with this, like from your own distance learning, feel free to leave them in the chat. You're more than welcome to, okay? Alrighty. So, AKA the period is 1. Great. Well, that's really useful information. Now we're going to keep on going here. What I'm going to do is just do this to give us some more space. Oh my gosh, there we go. You know what? That still all works. And this can just be erased. Great. So the next question is, what is the maximum height that the piston reaches? So I know you guys can't see here, but this should be 5.8. So we're going to write that down. Max height. So we're going to say max equals 5.8 meters. And the minimum height or in the question they're asking what's the lowest height that it reaches, is, and this is actually going to be 3.2, so that's right about there. So again, you guys can't really see because on my Desmos graph I didn't make the boxes small enough, but that's 3.2 for the sake of argument, or for argument's sake. And then basically they're asking how high is the crankshaft? That's our next question. So I'll tell you guys how high the crankshaft is in a second. How high is the crankshaft? Well, that's actually really easy to solve for, because what they're really asking for is what is our axis of symmetry? Our axis of symmetry is the line technically that's directly in the middle of the sinusoidal function that basically is halfway from the top and halfway from the bottom. And the crankshaft, as we see in the question, because it says here the piston of an engine moves up and down along a crankshaft in the middle, well, that tells us that the middle spot is where the crankshaft is. And there's a very easy way to solve that. So technically what we're solving for is the C term, because the C term tells us that axis of symmetry, basically. And all we have to do is C equals max minus min divided by 2. And very easily, that just gives us max plus min. Sorry, guys. My bad. 5.8 plus 3.2 divided by 2, which is equal to 4.5. So we've now solved for quite a few things. We've got our period, we have our C term, which is also known as the vertical shift, and we know our maximum and minimum height. So up next, we're going to be asked what is the equation of this problem, of this particular graph. So the last two things left for me to solve are the K value, the D value, and the A value. So again, let's kind of go over what all of that means. The A is the amplitude, and the way to solve for that is actually kind of just the opposite of how we solve for C. So instead of max plus min, for A it's max minus min divided by 2. Divided by 2. Let's move all this up a little bit. So max minus min divided by 2 is A, and that's 5.8 minus 3.2 divided by 2, which is going to equal 1.3. And then for the K value, we have the period already, so we know that the period of a function, especially when it's in radians, and I did this in radians because we're in grade 12, so we're learning in radians, it's going to be 2 pi over K. And in this case, we know that the period is 1, so this equals 1 equals 2 pi over K, and then therefore K equals 2 pi over 1, which is also just 2 pi. Wonderful. And then last but not least, let's talk about the phase shift. So the way that we determine the phase shift, guys, is actually pretty easy. In this case, it's pretty easy is what I'm trying to say, because we can see that if I was to call this a cos function, it actually at the 0 point, I mean on x axis, is starting right at the top of the amplitude, at the top of the function, I mean. So if I was to name this a cos function, we could actually just start it without any phase shift whatsoever. So let's start this out as a cos function. So let's do that. So we know that the amplitude 1.3, and we know that it's a cos function because it's starting at the top. And in that case, I can just go right ahead and put my bracket here. I know that my K value is 2 pi. And because it's a cos function, there's no shift because I'm starting at the 0 point exactly where I need to be. So with that being said, I just put an x here. And we go plus 4.5, which is the C term, which is also the middle line here, which I can show you guys actually. I'll show you guys where that is. So right here. So this is 4, 5. So this would be the middle point. If you think about it, like the graph is perfectly symmetrical around this point. Okay, I'm going to erase that just so that it's not confusing anyone if they're just popping in right now, but that's basically what we're saying is the C term. Okay, so if this was a cos function, this is what this would be. Sometimes teachers ask you to write this as both a cosine and a sine function. So actually keeping that in mind, I should put back my thingamabob here. So if this was a sine function, what I now need to do is find the point at the halfway point, because we know that sine functions start at the halfway point. So you can do this one of two ways. You can either make it a negative sine function. So if I was to start here, right, that would be a negative sine function. So it would look like this. Y equals negative 1.3 sine, everything else stays the same, right? But 2 pi, and then we've got x, and this would be moving over by, actually, because I didn't label these, you know what, we're going to do a regular sine function because this actually will not make sense. So 2 pi, we're going to do a regular sine function starting here because I actually don't know the exact numbers. So this is 0.5, 0.6, 0.7, 0.8, 0.9. So then this should technically be at like 0.75, right? 6, 7. Okay. So y equals 1.3 cos 2 pi, do like this, x minus 0.75. And that's not a cos function. Guys, sorry about this. My goodness. Why am I confusing you? 1.3 sine 2 pi plus 4.5. Okay. So you guys, that is that. And that is basically the main parts of this question. The next part of this question, I actually found this online. It's a really good resource, but it says basically, what would you expect to happen to the graph if you rev the engine? So if we think about that, if you're revving the engine, you'd probably get a shorter period because you'd have faster movements and you'd have more cycles. And then what would you expect to happen to the graph if the crankshaft was lower? Well, then we would just shift the whole graph downwards. Okay, guys? So that is something to keep in mind. Just going to go to the next thingamabob here. So let's go to this question here, you guys. So let's just fix this. Oh, quickly. Why are my buttons not working properly today? There we go. Okay, so hopefully you guys can see that okay. I'm going to try and keep it large enough that you can still see what's going on. But let's type in the question here. So the height of the tip of a propeller blade over time is shown by the graph below. So question A is, how long does it take for the propeller to turn once? Great, so let's talk about that. Again, let's move this over a bit. And just move this up. Great. Okay, guys, so how long does it take for the propeller to turn once? Well, what's really important for us to remember here is that what we're really being asked is, what is the period? And the way that we can determine that is just pick two spots and find out when it gets back to that spot. So I'll show you what I mean. I'm going to pick this spot because it's right on a number. And I'm going to look here and see when I get right back to that same spot. And that is, because this is time, I should have said that, time in seconds. So this is 2 seconds away. So we know that that's 2 seconds. And that 2 seconds is also the period of this graph, because that's how long it takes for it to go through one full cycle. So what is the max height reached by the tip of the propeller? So in this case, again, I know you guys can't really see the graph because I redid this on Desmos because the graph of what I found this on was very small, but this is 490. And really when they're asking what is the max height, they're asking to what point does the graph go? And in this case, we know that that's 490. And this is in centimeters. Height in centimeters. Cool. And then they want to know what is the minimum height. And that right there is 250. So again, I know you guys, it's kind of a small graph, so you can't really see, but that right there is 250. Great. So after we do this question, I'm going to kind of go over what my steps are in terms of solving these problems, because they're actually not that hard, but a lot of people find them really difficult because no one ever teaches us the step-by-step way to solve them. There's actually a really easy way to do it. Okay, so we got the min height. Now they're asking, how high above the ground is the center of the propeller? Well, that should be pretty easy for us to find because as we know, that's really just asking us for our C term, which is 370. Kind of like that. Okay, great. Well, how do we solve for that? It's actually not that hard. Again, we are looking for our midpoint. That's all that's being asked, right? So our midpoint, which is another way of saying the C term, is the max plus the min divided by 2. And that's just going to be 490 plus 250 divided by dose, and we get 370 centimeters, which is great. Up next, we've got how long is one of the propeller blades? And this is actually an interesting question that you wouldn't get too often, but again, sometimes teachers get super creative and expect you to know this kind of stuff. So if we think about it, one of the propeller blades, if we're thinking of this as a propeller, right? One of the propeller blades would be like that, right? So it would be from the midpoint to the max. So all I have to do is just say 490 minus 370, and that's going to equal 120 centimeters long. Okay, so let's go ahead and solve the actual equation of this graph. Okay, guys? First things first, and this is what I was saying, like I'm going to show you guys how I solve equations like this, because it actually really is not that hard. I'm just going to make this smaller. Okay. So let's talk about my foolproof steps for solving these types of equations. So steps. First things first, I want to get all my information as much as I can. So I'm going to write down stuff that's really easy to find. Max, min, I'm going to write down the period, and I'm going to determine whether I want to, actually let's just do this first. So we know that the max is 490, the min is 250, the period is 2. And then I'm going to use this information to my advantage. But what I also want to do, so step 1 is here, state knowns, or what you know, state known info. This is the info that we do know. Next, we're going to do step 2, which is solve for A, C, and K. So for A, the amplitude is max minus min divided by 2, which in this case, 490 minus 250 divided by 2, which is going to be 120. And then the C term we already have up here, so I won't solve that again. It's just 370. And then the k term is going to be, actually we should write it like this. The period is 2 pi over k, and the period in this case is 2, so we know that k is going to be pi. So I've now solved some pretty key factors. What I'm missing though are two things. First, what I want to do, so in my step 3, I'm going to decide sine or cos and find the phase shift. So the reason that this is together is because when I'm deciding whether it's sine or cos, that's how I can actually determine if there's a phase shift or not. In this particular graph, I'm going to use a sine function because it starts at its midpoint, which is how sine functions start. If it was that I wanted it to be a cos function, I would have to do a phase shift because then it would start here, like right there. I'm using my mouse, that's why it's kind of coming out wonky. So because I want to make a sine function where it starts at its midpoint, that's where I'm going to start it. If I wanted a cos function, I would have to start it right here. Okay, guys? So that's really the key. And what I'm going to show you now is that in this case, I'm going to pick sine, and my phase shift is going to be 0 as a result of that because I'm starting it there. So my sine equation would be, where is this? 120, and then sine, and the equation would be sine, and then pi x plus 370. So what if this was a cos function? I'm going to give you guys about 30 seconds. See if you can solve it if it was a cos function, then we'll go over that. Okay, guys, give me about another 30 seconds there. Okay. So in this scenario, because we're trying to convert it to a cos function, I'm going to see where my first maximum peak is, and I'm going to look at where that falls on the x-axis. At this point, it falls at 0.5, and that's 0.5 in the positive direction. So what that means for my cos graph is that it's going to be 120 cos pi x minus 0.5 plus 370. Okay, you guys, so these are not as crazy as they look. As I said, if you follow the steps that I've shown you here, you can always get the correct answer. Okay? Alright, so I'll let you guys write that down, and if anyone has any questions, they're more than welcome to ask. I'll leave that up for about a second there. Wonderful. So let us go ahead and talk about a couple other things. So what I need to quickly do here first is go to Desmos, because I actually thought I had created the third graph and apparently I didn't. So let's do this. So guys, bear with me for a second. I'm just going to get you guys the graph here. Okay. So let's get these numbers checked in here. One thing about using Desmos, you guys, is like if you're watching me do this right now, it's really important that you make sure that you're in radians when you're in grade 12. Like you see here, I've got it in the green on radians. Oh. Desmos can also be super annoying sometimes, so that's fun. Okay, great. There we go. Perfect. So in this particular graph, I'm just going to do this. Something like that. And we're going to bring that into our bit paper here. Oh, there we go. So, upload the files, upload this, and be ready to party. So, okay, let's look at this now. Obviously, you guys saw me plug in the answer, but that's okay. We're still going to use this to learn. Okay guys, so again, let's follow the rules that I was showing you. When you're trying to find the equation of something like this, it's actually not that hard. Again, you want to follow a couple main steps. Step 1, show info. So in this case, let's go ahead and get the info that we need. So we've got a max of 19 right here. We've got a min of 11. We have got a period, which is very easy to determine because all you need to do is pick two spots that are exactly the same and find out how long it took you to get from here to here. So in this case, it took us, so if this was at 3 and if this was at 9, then that period is 6 minutes. Okay. Alrighty, you guys. So what we've got here is, now all we need to do at this point is our step 2. And what that is going to be is find amplitude, vertical shift, and our k value. So let's start with amplitude. That's max minus min divided by 2. And that's going to be 19 minus 11 divided by 2, which is -4. Oh, hold on a sec. Sorry, that's just 4. What am I talking about? Then we've got our C term, kind of the same thing, max plus min divided by 2. And that's going to be 15. And then our k term, which is going to be, oh, actually we need to write it like this, period equals 2 pi over k. The period is 6, so this is just going to be this. And then when we rearrange this, we get k equals 2 pi over 6, which can be reduced to 3 pi over 6. 1 pi over 3. Okay, so now we've got 3 parts of our situation all figured out. And what's left to do is determine, do we want this to be a sine function or do we want this to be a cos function? And whether or not that information will tell us if there's a phase shift. So in this case, remember that most cos functions start at the top. But if you have a negative cos function, it can start at the minimum value. So in this case, I'm going to use a negative cos function. All that means is that my a term, instead of being positive 4, is going to be negative 4. And I'm going to have a cos, obviously. And then we use the rest of the information as is. So we get pi over 3 x. There's no phase shift because it's starting at the 0. And we get plus 15. Okay. So there we go, guys. One more situation solved. Okay, so I'll leave that up for a second. And if anyone has any questions, feel free to drop them in the chat. That's what we're here for. Okay, so now we've done a bunch of these questions where you've got obviously a graph that you've been given that you've been asked to graph, to find the equation for. One thing before I move on that you really have to be aware of is also what these equations mean, right? Like the amplitude tells us how much of a vertical stretch there is. This tells us there's a flip along the x-axis. This tells us the vertical stretch. This tells us there's a horizontal stretch because it's in the form of a fraction. If it was not in the form of a fraction, it would be a horizontal compression. This tells us the vertical shift. A couple other things that we want to note. What's the domain is something that you'll get asked a lot. The domain in this case, assuming that this is going on in perpetuity, obviously if these are kind of like that and you got your x and your y, then the domain would be x is the element of all reals with no exceptions. And then the range is actually between the max and the min. So you go y is the element of all reals. And then from there you would go, in this case it's 11 is less than or equal to y, and then is less than or equal to 19. Okay, hopefully that makes sense for you guys. If you have any questions, just let me know. But we're going to move on from this question. So I thought that I just wanted to go over that stuff quickly with you. So there are a lot of different types of questions that you could get asked in this unit. A lot of them are just dumb, in my opinion, like things that you'll never need to really worry about ever again. I don't know why, honestly, there's such a heavy emphasis on sinusoidal functions. I think that like they are useful in one sense, but as someone who's taken both biology as my degree and business and done the math for both, sinusoidal functions are not really something you need unless you're like a physics major for the most part. Obviously, we do use them in some biological functions, but again, it's not like you need them for the most part. Anyways, that's my rant of the day. Not really important, but it's okay. Here is this. Let me just move this over. Okay, so let's take a look at this now. I'm going to erase some of this stuff quickly. Alrighty. So let's say I had a graph with the following things. So let's say that this is 0, 0, and this is 2, 4, 6, 8. Oh, that should be an 8. And we've got 2. No, we should make this 2, 4, 6, 8, 10. So here I've got, basically they're asking us the water. Let me put the question here. And actually, you know what? This whole thing is trash. I'm just going to get rid of all of it. I apologize, you guys. Didn't mean to completely ruin everything. We're going to fix all of this in a second. Just give me one good second. Nope, this one. Expand. Yes, this is what we're talking about right there. Okay, so let me put these lines in just to make this make a little bit more sense for us. So that is annoying. There we go. And then say we start this like here. Okay, now we're talking business. Just put in my... Okay, so let's say this is 0, 0, and we'll do this. 2, 4, 6, 8, 10, 12, 14, and 16. And then on this side, we've got 2, 4, 6, 8, 10, yada, yada, yada. Okay, 2, 4, 6, 8, 10, 2, 4, 6, 8, 10. Okay, so, alrighty. And the question is saying, the water level in Ocean Harbor is 5 meters during low tide and 8 meters during high tide if it takes 8 hours to complete one full tide cycle. Basically, the next part of the question is A, sketch 2 tide cycles starting at high tide. Okay, this is actually not too hard, but this is the kind of question that a lot of teachers will give. So let's just move this over. So I actually find that this, damn it, this thing that we're using right here can be a little annoying sometimes. For our online tutoring, we actually don't use this service. We use something else that's way better, but the thing is that we are, because of the way that this is set up, it's just easier for me to use this for the live stream right now. Anyways, point of the story, they want us to sketch 2 graph cycles. So a couple things we know here and we want to write down, obviously. Max is 8, min is 5, and the period, which is how long it takes for one cycle to happen, is 8. Okay, so let's go ahead and sketch these on here. Let me fix this real quick. And they want us to start at high tide. Oh my gosh, what am I doing? They want us to start at the high tide, you guys, which is cool. That's fine. So at time equals 0, we're starting at 8. And let me use a different color to make this a little bit more obvioso. So there's that. We're starting at 8. And then we know that overall the period is 8. So that means that for it to get back to where it was, it has to be at 8. And we know that on a standard cos function, it reaches the minimum halfway through, because this is pretty much how this works. Like, this is standard no matter what kind of coast function you're doing. It takes half of the period for it to go to the minimum. And then basically you'll have halfway between there. So one thing I want us to solve for, a couple things that I want us to solve for. Also, this is 8. Okay. So first let's solve for the C, because that's going to give us our middle exactly. And all I have to do is 8 plus 5 divided by 2, which is going to give us 6.5. So I can actually just put that middle right here. So that's there. That's there. Great. Alrighty, guys. So that's that. Then we're going to get our A term, which is A minus 5. 8 minus 5 divided by 2, which is just 3 divided by 2, which is 1.5. Cool. And then we can solve for K by doing 2 pi divided by, no, I'm going to do this. So we've got our period equals 2 pi divided by K, which is going to be 8, 2 pi divided by K, and then this just becomes K equals 2 pi divided by 8, which is 1 pi over 4, pi by 4. Great. Okay, guys. So, anyways, they want us to sketch 2 cycles, so let's go ahead and get the other one all the way to 16. There we go. Halfway there is going to be here. And same situation. So this was not too hard. It's very quick to sketch 2 cycles, because if you sketch 1 cycle, you can just double it. And I'm going to connect my points. Oh, that last one leaves a little bit to be desired, but that's okay. So anyways, we did that. Now they want us to determine the equation of this function. So let me put that here. Oh, I probably should put that in black to be fancy. Oh, it's not happening, so we've already gone pretty far in terms of determining the equation. The only thing that we need to double check is this a coast function? Is this a sine function? So obviously when it starts at the max, it's going to be a coast function, you guys, okay? Which is not too crazy to think about. So in this case, it starts here, making it a coast function, and as a result of it being a coast function, there's no phase shift because nothing moved, right? So we've got y equals 6.5 cos times pi by 4 x, and you can write it with the extra bracket or without, it doesn't really matter, plus, oh, 1 second. Oh, I wrote 6.5 in the wrong spot. My bad. There we go. 1.5. And then this is 6.5. Okay, you guys. So again, nothing too crazy. That's our function. Now, this type of question gets a little bit nuts in the next step, which is why I chose this one, because I wanted us to talk about how all of this comes together in the word problem world, which is where things get a little annoying sometimes. So over here, so if it says if low tide occurs at 8 a.m., at what time would you expect it to be high tide? All right, guys, so let's think about that. 1 period is 8 hours. That means how long it takes to get from the high tide to the high tide. But how long it takes to get from low tide to the high tide is half of that. So there are 4 hours between low and high tides. And what that really means for you guys is that if it starts at 8 a.m. plus 4 hours, So that's 9, 10, 11, 12. Then it's 12 p.m., which is the same day. Okay. Now, let's make this one step harder. Keep on erasing over here. Now this is where things get real interesting. So I'm gonna make a little box here. So let's say if low tide occurs at 8 a.m., what would you expect the height of the water to be at 6 a.m. the next day? These are the type of questions that teachers love to give. I don't know why. I don't know why they enjoy marking them. But I mean, I guess it's obviously part of the curriculum, so that's why. But personally, if I was a teacher, I would just skip over these kind of questions because I think that they're annoying. But hey, that's just me. It's also why I'm not a teacher and why I'm a business person instead, because I get to choose this kind of stuff. So 1.5 cos, mind you, that's not to say that being a business person is always the better choice, because there's a lot of other stuff you got to do in your life as a business person. Anyways, guys, point of the story is, because I know everybody's raring to ramp this up. So if the low tide occurs at 8 a.m., what would you expect the height of the water to be at 6 a.m. the next day? Now, there's a couple things you want to think about. First of all, let's think about this. 8 a.m. plus 24 hours is 8 a.m. the next day. But we need 6 a.m. So to get to 6 a.m., we're going to go 24 hours minus 2 hours. Okay? So that means that 22 hours have happened. They've elapsed. Wonderful. So now, if our function here is actually a function of height, is height as a function of time, which is what it is. Another way of writing it is like this. X is time, right? So we can just write it as t instead. And then I take that information and I just plug it in. So I go y equals 1.5 cos times pi by 4 times 22 plus 6.5. I'm just going to roll that down a bit. So erase this bad boy. And if you ever need graph paper for this kind of stuff, mathaids.com actually has really good stuff. That's where I got these graph lines from. I also recommend, like, I've seen people actually scan graph paper into their computer as a PDF, and that's another great way to do this too. Okay guys, so let's plug this stuff in. So 22 divided by 4, because we're actually doing all of this in BEDMAS, right? So 22 divided by 4 is 5.5. So here you've got y equals 1.5 cos 5.5 pi plus 6.5. And remember that you want your calculator to be in radians. So make sure you're pressing your mode button going to radians, and you go cos of 5.5 pi. Oops. Which is 0. So 1.5 times 0 plus 6.5, and then you just get 6.5, and that means that the height is going to be approximately 6.5 meters. Alrighty. So hopefully that's helpful for you guys. Again, these are just, basically I'm not showing these to you just so that you can see like exact examples. It's more so that we can build strategies on how to solve stuff like this. So we're going to do one more lesson next week on this stuff, at least one more for sure, because there's still other types of word problems that we haven't dealt with in today's stuff. But I hope that today's lesson was helpful for you in terms of being able to solve these kind of problems when you have been given the graph but not the equation, and actually solving for the equation from the graph. I find that a lot of times people find that confusing. And then next week we're also going to do some more using the pi stuff, like using radians, because that's where I find a lot of people, even who understand how to do this unit, tend to get mixed up a little bit. And then other than that, you guys, we are all wrapped up for today. We zipped through that stuff today. If anybody has any questions, feel free to leave them in the chat. I'll be around for another couple minutes. And then we can go from there. All right. So if you have any questions, drop them in the chat. And if not, I will see you guys next week. I hope you have a great week. And I look forward to talking to you guys again soon. I heard that they're reopening the province a little bit, so I don't know if that means that they're going to reopen schools. I doubt it, but then again, these crazy cats, who knows what they're doing. And I hope you guys are having a good time in quarantine, staying safe, and I hope to hear from you again next week. So talk to you guys soon. Have a good one. Bye.